Hello everyone and welcome to the fifth and final part of our complete AutoDock CrankPep Masterclass series. Over the last 4 videos, we have installed our system, we ran the global blind docking, we visualized the structure using PyMol and configured user-defined grid boxes. Today we are looking at the most advanced and highly accurate docking technique available, which is known as template-based peptide docking or co-crystal based peptide docking. By feeding ADCP an existing structural template like co-crystal peptide from a homologous protein, we can bias the genetic algorithm to explore conformation that mimic a known biologically active binding pose. This dramatically increases your docking accuracy and ensures your results are backed by existing structural biology. Normally, the journal requires the template-based docking, which means a template is already attached. We will replace that template. We will use that binding site and dock our own peptide with that specific position. So let's start. First of all, open Ubuntu. We installed it in our first section. I have placed the video description link in the video description. You can view it. Once the Ubuntu installed, first thing you need to do is activate our window. We have created this environment in our first lecture. Micro MAMBA ADCP suite. Copy this command, go to Ubuntu terminal and paste it and press enter. It will activate the ADCP suite environment. Minimize this window. The second thing is choosing the working folder. This is my folder, test. This is on the desktop. Open this folder. In this folder, we have a protein 3Q47, which we downloaded from the protein data bank. Click in the address bar. This is your address. Copy this one. Go in the Word file. This is the template. What you need to do, first of all, from the start, type cd space /mnt / make this C small, delete the colon, delete the backward slash, replace it with the / and rest, delete the backward slash and replace it with the /. Do this with all the slashes and you will get the path of your current working directory. Then copy this path, go to the Ubuntu terminal and paste this path and press enter. Now you are in this working folder. Type ls and you will see 3q47.pdq is present in this window. Minimize this window and now minimize this one. So this is our protein 3q47. This is a hybrid protein which contains the protein as well as a dog peptide. To separate them, we will use the MGL tool. Go to the start and type AutoDock tools. Open it. Minimize this black window. The software is open. Maximize it. Go to the file. Click on the read molecule. Go to desktop. And again here the desktop folder. In desktop we have folder test. Open this protein 3q47. The protein is open. Click on this plus sign. It has two chains B and C. The B is protein and the C is the peptide. The first thing we need to do is edit. Go to edit and delete the water molecule. These red one are water molecule. The water molecule make the protein inert. To make it active or reactive, we need to delete the water molecule. So delete all the water molecule. Now it is left with the chain B and chain C. The first thing we need to do, separate the chain B and save it as a protein. For this one, select this circle. It will become yellow and the protein C chain is selected. Go to edit. Then click on delete and delete selected atom. Click on continue It has deleted the peptide chain. Now we only left with the protein chain. This is our receptor. To make it readable by ADCP, we need to save it in the PDQT format. To saving it in the PDBQT format, first we need to make it reactive or attractive for the peptide. For this, the first thing we need to do is add the polar hydrogen. Go to the edit, type hydrogen and click on add. In add, click polar only and click OK. Polar hydrogen has been added. Now we need to add the charges. Go to the edit, click on the charges and add Coleman charges and click OK. Polar hydrogen has been added and charges also been added. Now go to the grid, click on the macromolecule, click on the choose. Click this protein and select molecule. Click OK. The new window will automatically pop up. Go to the desktop. In desktop we have a test folder and save this molecule as a receptor. Receptor.pdbqt. Please remember this name. We need to use this name in our command and save the extension as pdbqt and save the protein. So our protein is ready. Now we don't need this protein. So simply select this one, go to edit, click on delete and delete selected atom and continue. Okay, now minimize, go to our test folder on the desktop. You can see the receptor.pdqt has been generated. Now our next target is to isolate the peptide from this protein. Go again in the file, click on the read molecule, select this 3q47 protein from the desktop in the test folder. First of all, delete water molecule, go to edit and delete water molecule. Water molecule are deleted, click on this plus sign. Now we have chain B and chain C. Select the B chain, click in this circle in front of chain B. The chain B has been selected. Go to edit, click on the delete and delete selected atom. Click on continue. The protein chain has been deleted and you can see now we are left with the peptide. This is our peptide. You can see this is 1, 2, 3, 4, 5, 6, 7 amino acid peptide. Simply go to the file. In the file, click on the save and write pdb. From here, change the name as co-crystal underscore pep.pdb. Pep.pdbqt and click OK. It will save this peptide as a PDB format. Now close this one and click this one. Go to edit, select this one, delete and delete selected atoms. Click to continue and this molecule has been deleted. Now we in our folder we have this is not in our folder. Let us check where it is saved. File preferences set. It is saved. We forget to set the working directory, so it has saved the file in user.make. So we need to go to our desktop, see users mic. So here is our co-crystal peptide. So I'm going to cut this file from here and going to place it in the working directory. So we have the co-crystal underscore pep.pdb and receptor.pdbqt. Now we have to make this peptide as a ligand. We need to tell that this is a ligand, not a PDB, not a receptor. So we will go again in the AutoDock tools, we will now go to the ligand, click into input and open. This time from the desktop in our folder test, we will open from this select PDB file. We will select co-crystal_pep.pdb and open it. This is the peptide. Now go to the ligand again, check the torsion, set number of torsion tree, click on the maximum, dismiss and select as ligand output. Save as PDBQT. Go to the desktop again and test. Select the PDBQT and save the name and co-crystal_pep.pdbqt and save it. So we have saved the peptide as a ligand. So in this folder we have two PDBQT files. One file as a receptor.pdbqt and the other file is co-crystal_pep.pdbqt. Co-crystal_pep.pdbqt will work as a co-crystal ligand or a template, and receptor will work as a protein. Now this is our working command. We will use AGFR tool. R is a receptor, receptor.pdqt, minus L is your crystal, ligand. Ligand will use as co-crystal pep.pdbqt. It will use the ASV version 1.1 and it will generate the output file as a receptor, my receptor.trg. The detail is description in here, you can read. I will upload this file in the video description section as a download link of GitHub. You can download and copy and paste this command to run. Simply copy this command, go to your Ubuntu terminal, paste this command and press enter. Now it is now initiating the grid box generation. It will use the grid box from this co-crystal ligand and generate the grid box information. The grid box generation is completed. It took about 11.5 seconds. It took a very short time because it only generated the box against the template, against the co-crystal ligand. It has not screened the whole protein. It just screened the binding site that was previously docked with your peptide. Now we are going to run a small test in which we are going to use ADCP. It will override the existing input file. It will use the target file which is named as my receptor.target file. This is our sequence of your amino acids, which is your peptide. You can change the peptide sequence. Just use simple one letter peptide sequence like glycine, cysteine, thymine, kinase, etc. 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 So you can simply type the one letter amino acid sequence. The good thing about ADCP is you don't need to worry about the structure. Just type the sequence. It will automatically form the 3D structure. You don't need a 3D structure here. Now it will make the cyclic structure of this peptide and it will run 5 independent Monte Carlo run, and it will take about 0.1 million steps, and the result will be pasted in the test1 working directory and the name will be as example1. Let's have a look in our folder. This is our test folder. It contains these files which are basically my receptor target file, and we don't have a working folder right now. So what you need to do, simply copy all these commands, paste in the Ubuntu terminal and press enter. The docking has been initiated. It will complete the docking depending upon the computer speed and number of poses it has generated. The docking is completed. These are the result of our docking. You can see this is our best pose minus 2.9, and from here the values are 0 or positive, which means they are not properly docked. The more the negative, the better the result is, which means minus 2.9 is better than minus 2.5. So the best pose is minus 2.9. Our docking has been completed. If we go to our test folder, the new folder has appeared. It contains our results. These are the example summary, the DLG results. Open with the notepad or notepad++. These are the results which we just saved, and these are the doc posts which the result are generated. All the poses, like if you see in this notepad file, about 41 poses has been generated. All the poses are stored in this output file. In our part 3, which is about visualization in the PyMol, we have explained that how you can use this output file to produce and see the ligand peptide interaction, see the hydrogen bond, see the hydrophobic interaction, and other interacting molecule. You can refer to this part for the visualization of these results. I have placed the video link in the description section. This brings us to the end of our complete 5-part AutoDock CrankPep Masterclass series. Let's look at what we have achieved together. We started from zero. We installed Ubuntu, Linux, and ADCP. We used the search space of blind docking. We analyzed the result in PyMol. We isolated the pockets and calculated hydrogen bond. We optimized our local coordinate using focused gridbox, user-defined gridbox, and finally we learned how to run template-based or co-crystal-based docking. Now you are enabled to possess the complete toolkit to run high-level publication-quality peptide docking simulation on your own machine. If you like this series, please hit the subscribe button and share this playlist with your researcher and students. Thank you so much. Take care and goodbye.